Welcome grade 11s to physical science. My name is Gillian, and today we are going to be talking about chemistry, atomic combinations actually. So what are atomic combinations? Combination is putting things together. Atomic is atoms. So it says what it says. We are putting atoms together. And we know that we have two kinds of bonding. That's covalent bonding and ionic bonding. And so we're going to look today at what is happening right in the very center of that bond. We are going to pretend that we are Ant-Man, and we're going to become really, really small, and we're going to zip right into those bonds and see what is happening. But before we start on our theory, let's have a look at some questions. So on my board, I have two questions for you. Have you ever thought about why substances behave differently? They could all behave the same, but they don't. So why don't they? So here's an example of two substances that I would expect to behave the same way. They're both oils, so coconut oil and sunflower oil. I would expect them to behave the same way, but they don't. If you put coconut oil into the fridge and cool it down, it becomes a white, hard substance, and you can't see through it. It's like almost milky. If you take it out the fridge and on a hot day you let it melt, it becomes a clear, see-through, very runny liquid. That's odd. So wouldn't sunflower oil do the same? Well, no, it doesn't. It's yellow, and all it does when you put it into the fridge is it becomes a little more dense and not as runny. Okay, that's strange. If you think back to a petrol station, maybe you've been in the queue for to get petrol in a car, and you look at the petrol that is coming into the car ahead of you. You'll see a vapor coming out of the aperture where the petrol is going in. It's like a vapor, you can see it. So pouring petrol makes a vapor, but if you pour water, it doesn't do the same thing. Have you ever thought why? Well, let's hope we can answer those questions as we go through today. Okay, so what are we going to look at in detail? We are going to, first of all, know our definitions. So we need to look at two definitions. We need to know them off by heart so we have an idea of what we are talking about. Then we're going to look at relationships. The relationship right in that center of that bond, we're looking at three relationships. The first one is bond energy and bond length. So how is the bond energy and the bond length related? We're looking at strength of the bond and the length of the bond. Okay, so how are those two related? And then atomic size and number of bonds. So how do those interact and what happens with bond strength and bond size and atomic size? A lot of things to think about. We are then going to tackle electronegativity and what exactly that is, and the fact that it allows a molecule to become polar. So we talk about polarity, and when we're talking about polarity, we have to speak about the change in or the difference in the electronegativity of the bonding atoms. Okay, a lot to get through today. So let's have a look at those definitions. So on my board, you will see a familiar graph. So this is the graph of potential energy, and we start off with two atoms that are pretty far apart. We measure their distance apart using picometers. So you'll see a PM over there on the screen. PM, it is picometer, and I have reminded us over here that a picometer is 1 times 10 to the minus 12 meters. Okay, so we are looking at extremely tiny, tiny, tiny distances. We call this distance that's between the two atoms, we call it R, Okay, so there's an R. I don't know if you can see it there. You'll see it with all the values. They say R equals, R equals, R equals. So it's a little r, and that stands for the internuclear distance. So what is internuclear distance? It is the distance between the two nuclei of these atoms. So I have got two hydrogen atoms, and in the center will be a nucleus for that hydrogen and a nucleus for that hydrogen. So we're talking about the distance between those two nuclei. Okay. So when we start looking at the interaction between these two hydrogen atoms, they are quite far away. And so R is equal to 300 picometers. They're quite far away. We then see that as we bring those two atoms together, that there is an overlap of orbitals and that a bond takes place. So this is a covalent bond. And you can see when you look at the shape of the graph, you'll see that the energy decreases. Can you see that? Right to that point over there where the scientists consider an optimal distance apart where the bond takes place. So at that point, the lowest potential energy, you can see here on the graph, it's negative 432 kilojoules per mole. That is the optimal positioning for a bond to take place. If we try and squash those atoms closer together, they don't like that too much. And you'll then see that the potential energy increases hugely, exponentially. And you can see here, they have shown those two hydrogen atoms are only 45 micrometers apart. And they don't like that. There is repulsion. We have spoken about that before. So what we are looking at then is we are looking at what is bond length. So bond length is our first definition. Bond length, what is that exactly? Well, it is the distance between the nuclei of covalently bonded atoms. Where is that? Because that could be at 300, it could be at 150 picometers, it could be at 74 picometers, could be at 45 picometers. We are determining this bond length at the point where the potential energy of the covalent, that should be bond, not energy. I'm just going to write here bond, is at its lowest. And where is it at its lowest? It's at its lowest over here. At optimal distance apart, at R equals 74 picometers. Okay, so bond length. What is bond length? It is the distance between the nuclei of the covalently bonded atoms. And that is at the lowest potential energy of the chemical bond. Okay, good. I hope we've got that one. Now, the next one is bond energy. Now, we come across bond energy again when we talk about exothermic and endothermic reactions. So, bond energy is quite important. We need to understand what it is. When a bond is made, energy is released, and that is called bond energy. To break that bond, we have to put the same amount of energy into the molecule to pull those two atoms apart. So again, we're looking at hydrogen, the diatomic molecule of hydrogen. We see that when a successful covalent bond is made, there is a release of energy, and that is over here. We see it here. Okay, we see it as positive, and there's another one which is negative. So when we have a bond which is made, the energy is released, and so it is a positive value. When we want to break that bond, we have to put energy in, and so it is a negative value. So what is then bond energy? How do we define it? It is the amount of energy required to break 1 mole of a particular covalent bond in the gaseous state. Now, you're going to say to me, why break? Well, how can we effectively measure energy that is released? It's quite difficult. So, it's easier to measure the amount of energy that is needed to be put in to break it. We know how much we're putting in to break those bonds. The second thing is we can't measure just 1 molecule. That's virtually impossible. There have to be a lot of molecules that we're measuring. And so that is why we're talking about 1 mole. 1 mole is a lot more molecules, and we can get a decent value for how much energy is needed to break those bonds. Okay, good. Bond energy, hope we understand that. Now, we want to move on to relationships. What are the relationships involved in this bonding? And the first thing we're going to look at is bond energy and bond length. There we go, bond energy and bond length. Okay, so we have a number of bonds here in this table, and we are going to order them from the smallest to the biggest in length. Okay, so in length. So here we go, the average length. I have highlighted a few. I'm going to write them down here. So we've got a hydrogen bond. Okay, its length is 74 picometers. How much energy is needed to break it? Well, an average of 432, and that would be kilojoules per mole. Okay. Right. Let's go to the next one. So the next one I want to go 74, let's go down to here, 101. Okay, so that is the hydrogen joined to a nitrogen, and 101. Let's just put picometers at the top here so we know what unit it is, and that's 390. Right, next one. Hydrogen and chlorine, and that is 127, and its bond energy is 428. Okay, hydrogen and bromine, hydrogen bromide, 141, 362. Okay, let's do the CC bond, carbon to carbon. Its length is 154. To break that bond is 345 kilojoules per mole. And then the last one, let's take chlorine and chlorine. So the diatomic chlorine molecule, 199 picometers, and it takes 240 kilojoules to break that. Interesting. So let's look at this. If we look down the length or down the column and we see the length, we can see that it increases. So the distance between the atoms is increasing. The distance between nucleus and nucleus, it's increasing. Right, but now what's happening on average to the bond energy that is required? So if we look over here, we start off with 432 and we end with 240. So this is decreasing. So if you look down this column, you see that the amount of energy that is needed to break the bond is less. So the longer the bond length, the smaller the amount of energy needed to break it. That's telling us something. That's telling us that the longer the bond, the weaker it is. So what conclusions can we speak about when we're talking about bond length and the amount of energy that is required, the bond energy? What is the relationship? Well, we can say that the longer the bond length, the smaller smaller the bond energy. Right, grade 11s. Let's take a quick break. When we come back, we'll have a look at more relationships. Welcome back, grade 11s from the break. So, before the break, this is what we did. We saw that if the bond length is long, if it's big, if the distance between the nucleus and the nucleus of our atoms is big, that the strength of that bond is not so great. And so the bond energy that's needed to break that bond is smaller. So that's the relationship. Our next relationship is about the number of bonds that are formed between atoms. So bond energy and number of bonds, what is the relationship with those between those two entities? So first of all, we need to know what bond order is. So we speak about bond order quite often. Bond order is telling you how many bonds are between the atoms. So it is the number of bonds, so a single bond, a double bond, or a triple bond that exists between two atoms. And so if we have a single bond, the bond order will be 1. If we have a double bond, the bond order will be 2. And if we have a triple bond, the bond order will be 3. Okay, so let's have a look then at what a molecule is going to look like when it has got a bond order of 2 and a bond order of 3. Okay, so we have got here on the screen bonds between carbon atoms. So you can see that there are 2 carbons. They are the black balls on that side. Okay, the black spheres. Those are the 2 carbon atoms. And you can see in the first one, it has a 1 above it. And that is telling you that it has a bond order of 1, and therefore it has 1 bond only. Now this molecule is ethane. It's an organic molecule. You'll get to that later. And it has a number of hydrogens bonded to it. So you'll see these white spheres. They are hydrogen. So we have 1 bond here in ethane between the carbon and carbon atom. And I want you to have a look at the distance. Can you see, or the bond length, can you see that's 153,5 picometers? Okay, let's move on to the next molecule. The next molecule is also between consists of 2 carbon atoms, but now there is a double bond. Now this thing is called ethene. It's got an interesting name. It's called ethene, and we can see that it's got a double bond. Its bond order is 2. And look at the distance, the bond length between the carbons. It's 133,9 picometers. So we can already see that there's a decrease in bond length. Okay, the last molecule is ethine. Now, ethine has 3 bonds between the carbon atoms, and that is why its bond order is 3. And have a look here, 120,3 picometers. So that's telling us something. It's telling us that the more bonds there are between 2 atoms, the shorter the bond length. It is getting shorter. And we've seen already that if the bond gets shorter, the bond length gets shorter, more energy is needed to break those bonds. So let's have a look at the bond energy at the bottom of the screen. So it says 348 kilojoules per mole. Okay, that is for the single bond in the ethane. Then the next one has a bond energy of 612 kilojoules per mole. It's increasing. We would expect that because the bond length is decreasing. It means that there is more energy needed to break that bond. Then our ethine, which has 3 bonds, needs 837 kilojoules per mole to break those bonds. So can you see that if we increase the number of bonds between the atoms, the bond length decreases, and so more energy is needed to break those bonds, and so bond energy is greater. So let's have a look at how we can write this. The more bonds between the atoms, the shorter the bond length. Therefore, I'm going to write that in there. Therefore, the stronger the bond, the greater the bond energy. Okay, so that's something that is good to learn. Learn how to write this, because this kind of knowledge will be asked of you in a reasoning way. You have to reason through a problem, and you would then give this kind of written answer to explain why on a graph you would see the bond energy increasing as the number of bonds increase between the carbon atoms. Good. Let's move on then to the last relationship. This is quite a funky relationship. I love it. It's very interesting to see how these atoms behave. So we're now talking about bond energy and the size of the atoms. So now, this picture I have on the screen is covalent radii. It's also in picometers, times 10 to the minus 12 meters, also really small. So we're talking about the radii of atoms. And if we look along the period, so I'm going to start with this one here. So that would be number 2, period 2. And we're going to look along there like that. Have a look at the size of those atoms. Can you see that lithium is quite a large atom? And as we move along the period from boron to carbon to nitrogen to oxygen to fluorine, can you see that the general pattern is that the radii are getting smaller until we get to group 18, which is over here. Group 18, neon, suddenly gets really big again. Okay, let's have a look at period 3. So period 3, we're going from sodium to magnesium along there like that. So have a look. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. We see the same pattern. We see the same pattern of the atomic radii getting smaller. Now, that's not what I would have thought. That is very, very interesting. The same happens for period 4 and period 5. Can you see that? As we move along the period, if we look at the size, we see that the atoms actually get smaller. What about if we look down the groups? So if we go from top to bottom, down the group. So if we go group 1, if we go all the way down there like that, we can see that there is an increase in the radii. So we go from lithium to sodium to potassium to rubidium, and so on. We can see that there is an increase in the radii. Have a look there. Now that is what I would expect, right? I would expect that to happen, going down the group. And the same applies on this side. We can see that fluorine is really small, and then chlorine increases, bromine increases even more, iodine increases even more. So down the group, we can see very clearly that the atomic radii is increasing. But now, what can we say then about the decrease in atomic radii as we go from left to right along the period? That takes some thinking. So let's have a look at our thinking. So if we look along the period, like that. I've taken period 2. We've got lithium. I haven't taken all of them. It's lithium, carbon, fluorine, and neon. So I want to really look at lithium, carbon, and fluorine. The red circle is telling me that that is the valence shell, and the valence electrons are in there, the outermost energy level and the outermost electron. So we see that lithium, well, we know lithium's atomic number is 3. It's got 3 protons and 3 electrons. You can see the 3 electrons there. Then carbon is, let's count, 1, 2, 3, 4, 5, 6. It's 6. Its atomic number is 6. 6 electrons on the inside, protons on the inside, and then 6 electrons on the outside. But have a look here. So we go from 1 with lithium in the outer shell to 1, 2, 3, 4 for carbon. So there's 4. So the electrons are increasing as the atomic number increases, but they're staying in the same energy level. That is interesting. What it means is that the attraction, the number of protons is increasing, and the number of electrons are increasing, but they're increasing on the outside. That means that the attraction between the protons on the inside and the electrons on the outside is pretty strong. So those protons are attracting those electrons very strongly. And as a result, the volume of the atom decreases. Remember, the electrons create the space around the nucleus, and so if they are being attracted inwards, then the radius is going to get smaller. But what about when we go from period 2 to period 3? So the number of electrons and protons is increasing. Lithium is 3, the atomic number is 3. Sodium is 11. But now what happens is those electrons fill more layers. So if you look here, you can see that there are 1, 2, 3 layers. Energy levels, according to Bohr's atomic model. And so the effect of attraction, that attraction between the protons and the electrons, is not as great. And so that atom has got more volume because the electrons aren't attracted as strongly as the other atoms in the period. Okay, so how do we write this? This is what we write. As the size of the atom decreases, okay, so that's moving from left to right in the periodic table along the period. So as the size of the atom decreases, the bond length is going to decrease. And what do we know about that? Bond length decreases, it is then increasing in strength. And so the size of the atom, when it increases, that is down the group, we're looking down the group, the bond length is going to increase, and therefore the bond strength decreases. Okay, a quick summary then of what we have discussed. The shorter the bond length, the higher the bond energy. The more bonds between the atoms, the shorter the bond length, and therefore the stronger it's going to be, the greater the bond energy. As the size of the atom decreases along the period, the bond length is going to decrease, and so the bond strength increases, and the same, well, the reverse with when we're talking about down the group. If the size increases, the bond length is going to increase, and so the bond strength is going to decrease. Right, it's time for a break, grade 11s. See you later. Welcome back, grade 11s. I hope your mind is a little rested. We are heading in for the next set of theory, and this is about electronegativity. So now we're going to see exactly how these atoms interact and what they do with these bonded electron pairs. So first of all, we need to figure out what is the definition of electronegativity. So here it is. It is the measure of how strongly an atom attracts the shared pair of electrons in a chemical bond. Okay, so if we have got hydrogen, there is an overlap, and that overlap is where an electron is shared, and an electron is shared. So this electron from hydrogen can go all the way around into that shared part where they overlap, and can go into that, it can orbit that atom as well, that hydrogen atom. So there are two electrons, one from each hydrogen, that are shared. Now, what happens? That sharing of electrons is manipulated by one of the atoms involved in the bond. Some atoms are very electronegative. They are greedy, and so they will pull the bonded electron pair towards themselves. They pull it more strongly than the other one does. And so we end up with an electron cloud that sits over the atom that's more electronegative. We denote electronegativity by a big N and a big E and a big N, En, and then we will speak about a bit later how we find the difference between the two atoms' electronegativity. On the periodic table, we get given a lot of information, but one piece of information which is very important for you is it's labeled, it's given to you, electronegativity, and you can see it here. It is the number that is written on its side, and for copper it's 1.9. So if I look at hydrogen here, I will see on the side 2.1. What about oxygen? Oxygen is 3.5. Fluorine is 4. Okay, so that's quite a large number. What about lithium? Lithium is 1, only 1. Isn't that interesting that lithium has a lower electronegativity than hydrogen? Let's look at chlorine. Chlorine is 3. Bromine is 2.8. Iodine is 2.5. So, okay, so we've picked up a pattern there. It decreases from top to bottom in group 17. Let's see if it does the same in group 16. So oxygen 3.5 goes to 2.5 for sulfur, 2.4 for selenium, 2.1. Yes, it's also decreasing. So that's where we find the electronegativity, the measure of how strongly an atom will draw the bonded electron pair towards itself. Now, this has got a big influence over, and now we're coming to answering our questions right in the beginning. It has a big influence over how a molecule behaves. So the difference in En, or electronegativity, delta meaning the change in, values determines the type of the chemical bond. So first of all, it's going to be able to tell you whether it is covalent, difference now, whether it's covalent or whether it is ionic. It is going to be able to tell you more things about it as well. So if we're looking at covalent bonding, we have different types of covalent bonding where the bonded electron pair is pulled more strongly in some cases than in others. And that then affects what we call polarity. We get poles created. So this difference in electronegativity influences the intermolecular forces between the molecules, and therefore it influences the behavior. And when we're talking about behavior, we're talking about its melting point, its boiling point, where does it freeze, does it vaporize easily, all those physical behavioral characteristics of a molecule. Okay, so let's have a look at our very first combination of a like atom joined to itself. So we've got, what about this diatomic molecule? So a diatomic molecule is consists of two atoms of the same kind. We can see, I've given you a picture of how the orbitals overlap. Those are quite big orbital diagrams. We don't really use them, but it's quite an interesting picture to see. Here is another picture below of oxygen. And you can see that both oxygen atoms have got free or unpaired electrons. These ones at the top here are the lone pairs. Those are the ones that are already paired within the atom, and they are not really interested in the bonding process. So lone pairs, that's where they are. So there will be an overlap of orbital and two, because you can see that those two will naturally overlap, and then these two electrons will want to share an orbital as well. And this is how it's drawn in the center. You can see that there is an overlap of two orbitals so that sharing can take place. So we would know this drawing where we place two lines in between the oxygens to show that two bonds are happening here. In other words, there's an overlap of two orbitals. Now, oxygen and oxygen are of the same kind. They are the same thing. And so they are going to pull those bonded electron pairs equally. So we end up with a molecule which is non-polar. Okay, here's the word. It is called non-polar. In other words, they are going to pull those bonded electron pairs equally. So what is a non-polar combination or bond? It is a covalent bond, so we're talking about covalent bond, in which both atoms attract the bonding electrons equally. You can see that the difference in electronegativity equals naught, because if we put the values in and subtract them from each other, we have to get naught. They are the same. They are going to be pulling with the same amount of force. So a non-polar covalent bond, here is the example of hydrogen. The potential energy of the molecule is less than the separate atoms. We know about that. The electrons are shared, so there's a sharing to complete the first energy level. And there's the sharing, and they will share, so that's telling you about the covalent bonds. They will then share those two electrons equally, and so they will be, this whole molecule will be neutral. There won't be any charge on it because the electrons are evenly spaced around those two nuclei. But now what about when we've got two different atoms joining together? So here I have hydrogen and chlorine, and you can see, so this is a hydrogen chloride. If we have a look at our periodic table, we'll see that chlorine has got a value, an electronegativity value of 3, and hydrogen is 2.1. So if we place that into a formula, if you like, we do a sum, we are looking for the change in electronegativity. We say chlorine was 3. Hydrogen was 2.1. 2.1, sorry. What is that going to be? Well, it's going to be 0.9. The difference is going to be 0.9. So that is still a covalent bond, but it's weak. It's quite a weak covalent bond, weakly polar. Why is it polar? Because chlorine is still the more electronegative. It's going to pull those electrons over itself, and you can see here that more electrons are sitting on this side than on the hydrogen, and so that side becomes slightly negative because the electrons are going to be spending more time with the chlorine. And so we say that this is delta negative. It's a small letter delta. Delta negative, it means that that is the negative pole. Over here we have delta positive because hydrogen is most of the time without those electrons, and so that's the hydrogen side of this covalent bond is going to be delta positive, and that means it has a positive pole. So we say that this is a polar covalent molecule because it has poles. It is weakly polar because the difference is still reasonably small, and you can see here the difference in our electronegativity is less than 1. Right, a covalent bond in which electrons are pulled closer to the atom with a higher electronegativity. That is the definition for a polar molecule. Grade 11s, it's time for a short break. I will see you in a moment. Welcome back, grade 11s. Right, so we spoke about hydrogen chloride and how chlorine pulls those electrons, those bonding electrons over itself because it's more electronegative, and so we get a pole which is positive and a pole which is negative. We call it delta negative and delta positive, and because there are two poles, we call it a dipole. So have a look on the screen. You'll see here dipole. What does that mean? Di meaning 2. Here is the negative pole, the delta negative and the delta positive. Right, we are going to move on now to another covalent molecule, which is very, very polarized. We have the difference in electronegativity between the atoms involved is starting to get bigger, and we're going to look at what happens. So I have water here. So water, has 1 oxygen and 2 hydrogens attached to it. Now, for a molecule to be classified as covalent, it needs to have a difference in electronegativity of between or less than 1 all the way up to about 1.7, 2.1-ish. Now, the reason why I'm saying that is because people have done these experiments and have got this data, and sometimes there is a little bit of discrepancy. They don't always match. That's okay for us. We don't have to get too hung up about it. What we do need to know is that this end value can be from 1.7 all the way up to 2.1. After that, we're expecting an ionic bond, and we'll talk about that a little later. So let's look at this covalent bond. So this covalent bond of water, you will see the difference in electronegativity is greater than 1, but less than 1.7. And how does that work? Well, we have got a bond between the oxygen and hydrogen on this side, and we've got a bond between the oxygen and hydrogen on that side. And you'll see these red arrows, and the red arrows are showing that the oxygen is more electronegative than the hydrogen. And so it is going to grab those bonding electron pair and pull them over itself. So that the electron cloud sits over the oxygen mostly. Really, the hydrogen is such a small such a small atom that it is very much exposed. And so we just have this naked proton that kind of sticks out. We say that the hydrogen is naked because it has lost its covering, it's lost its electron to oxygen. That's how strong oxygen is. There are 3 atoms that are highly electronegative. One of them is oxygen. So if we look at the difference between these electronegativities, we're just going to look at the one bond. So I'm using values from our periodic table, not from this picture that you see. And oxygen is 3.5 and hydrogen is 2.1. We end up with a difference of 1.4. So you see there that the difference in electronegativity is greater than 1. And so we end up with a very covalent, a very strongly covalent molecule that has got poles, so strongly polar covalent molecule. This would be the delta negative side, and that would be the delta positive, and that's delta positive. Okay, so it is strongly polar covalent. It is very electronegative, and the other atoms are nitrogen and fluorine that are so highly electronegative, they make these very polar covalent molecules. Okay, what makes water behave differently is that it is asymmetrical. Its shape, if you remember, its shape was bent or angular, and because of its shape, it becomes asymmetrical, and it does the most amazing things. Its intermolecular forces are very different. We will come across intermolecular forces in another lesson. So let's have a look then. How do we end up with an ionic bond? So you can see here we've got this non-polar covalent bond. And that's chlorine, chlorine, it's the diatomic molecules, oxygen, oxygen, hydrogen, hydrogen, fluorine, fluorine. Okay, and the difference is zero, is naught. It's naught. Then we move on to the polar covalent bond, which is a dipole, and the dipole is two atoms covalently bonded, but there are very weakly covalent, very weakly polar covalent. And so they will have two poles, but the difference will be less than 1. Remember, we worked that out. Let me just write here. So the non-polar, the En, is going to be equal to naught. Over here, the difference in electronegativity is less than 1. Then we have those strongly polar covalent molecules. They're not in here, things like water, and their difference in electronegativity is going to be greater than 1. Now, what happens is when we get to ionic bonding, the difference in electronegativity is so great that that electron isn't shared anymore. It's actually dragged over and it is taken. And that electronegativity difference will be greater than 1.7. Remember I said all the way to, I made a mistake there, 1.7, all the way to 2.1. And then it becomes an ionically bonded substance. It's no longer covalent. So the difference in electronegativity tells you whether it is covalently bonded or whether it is ionically bonded. Also, the difference will tell you whether it is a covalent bond that is between a diatomic molecule, or if it is weakly covalent, or if it is strongly polar covalent. Now, just to finish off, why is polarity so important? It determines the way that the molecules interact with themselves, and so it will then show you behavior. And I want to show you this last molecule, which is very interesting because this is a polar molecule, but it behaves like a non-polar molecule, and the reason why is because of its shape. So the shape nullifies or cancels the poles that are created by the electronegativity of the atoms. So this is boron trifluoride, tri meaning 3, so boron trifluoride. This is a trigonal planar molecule. You can see that they are that the bonds are evenly distributed, and all those bonds are 120 degrees from each other. And so this is a really perfect shape, and so the delta positive and the delta negatives, the influence of those poles is cancelled because of its shape. Right. So, grade 11s, remember all these things that we have done. We've spoken about definitions. We've spoken about the three relationships. We've spoken then about electronegativity and the polarity that results. We have non-polar molecules. We've got dipoles, we've got strongly polar molecules, and then we've got non-polar molecules with polar bonds because they behave like a non-polar molecule because of their shape. Right, that is all for today. I'm hoping to see you another time, grade 11s. Goodbye for now.